Okay, yeah. Then welcome everyone to the weekly colloquium of the Instituto de Ciencias Físicas of the UNAM in Cuernavaca, Mexico. Our guest today is Professor Henning Schomerus from the Lancaster University in the United Kingdom. And let me say some few words on his vitae. Dr. Schomerus did his PhD at the University of Essen in Germany in 1997. And from 1998 to 2000, he was a postdoc with Carlo Benacker at the University in Leiden in the Netherlands. And from 2000 to 2004, he was head of a junior research group at the Max Planck Institute for Complex Systems in Dresden, in Germany. And since 2005, he's professor for physics at the Lancaster University in the UK. His research aims to uncover quantum phenomena occurring for electrons and photons in small quantum systems, in particular involving topology, disorder and interactions, and dissipation. This includes the study of topological photonic systems, such as lasers, topological insulators, and superconductors, and quantum many-body systems. Henning, thank you very much for joining us, at least virtually today. It would be a pleasure to have you here in person the next time again. And yeah, we're looking forward to your talk.
Thank you very much, Thomas, for your kind introduction and the invitation. And yeah, at least I was in Cuernavaca once 7 years ago, and it was a very nice event. So now at that time, well, what I'm talking about today is sort of an overview of research which actually panned out over the last 10 years. But at the time that I visited you, that was still very fresh and I wouldn't have much to talk about. And essentially what this is about different mechanisms to confine light within certain structures without using mirrors, in other ways using wave interference effects which are very systematic. And this can be carried out on many different platforms. So this introductory slide that has, for instance, light coming out of a hybrid semiconductor laser or out of exciton polariton device, or a pattern that you see with photons in something which is called a quantum walk. In all of these, you see different wave patterns, which seem to be quite characteristic and different from the speckle that you get in random system. So there must be some clever way to achieve these patterns. And behind this, there are some ideas from topology. Topology is a very broad field, of course, but there is a big effort in electronic systems to talk about the band structure of electronic materials. And what we do is lift these ideas and transform them or transfer them into the photonic domain. And what we are really interested in is how this then becomes a different thing, because photons behave different than electrons. And in some cases, this allows us to do something different, or different and maybe also interesting in a different way with them. So in terms of an introduction, topology has many different roles in physics, but the one that we are thinking of here occurs most prominently in periodic structures. And one place where it appeared quite early on in the game is when people investigated the electronic transport along the backbone of a chemical structure, where these dots here are essentially carbon atoms. So these are so-called conjugated polymers. They sometimes have semiconducting properties. And the reason is that they have a certain band structure that you can understand by looking at the tight binding model for this system. Now there are, on the chemical side, strong bonds and weak bonds, essentially double bonds and weak bonds, which are alternating. And what is not shown is all the other elements which are there. The transport is really going along here. And if you describe this in terms of band structure, then you start out with a periodic system that has a unit cell of 2 sites. And this repeats periodically. And if you write down the corresponding Bloch Hamiltonian, it will have 2 eigenvalues, which when you plot them as a function of, say, the wave number, draw out 2 bands. Okay, so this is this red band and this green band here. And they actually turn out to be symmetric in the simple model, where you only consider the couplings between the different points or atoms. This is to do with the symmetry. It's known the chiral symmetry, and the chiral symmetry is going to be important for the remainder of this talk. Now, the topology arises because you can define the unit cell in two different ways, one's with a strong bond inside the unit cell, or one's with a weak bond inside the unit cell. If you just look at the band structure, this does not make a difference. But if you bring these two different types of configurations together, you find that it doesn't quite match together. There is already in the structure something going on, but also in the band structure, essentially, or in the energy spectrum, something will happen, namely a new state appears. It's sort of putting an extra site into this symmetric energy structure. There needs to be an extra site, an extra state, and the only place to preserve the spectral symmetry is to have this state at zero energy within the band gap. This state has three interesting features. And two of them are actually known to most people, and the third one will be quite important to us. The first one I already said is that this is at zero energy, at a sort of a symmetry protected energy in the system. The second is that this state will be confined to the interface, which is clear because there are no states, if you go deep into the bulk of these two phases, there are no states that you can populate. You are working in the band gap, so this has to decay exponentially. And the third feature is that this state is only sitting on every second site. So you, in this case, it looks like you have added a red point into the structure, and then this extra state also takes all the weight of this. It's distributing it a little bit across away from the interface, but it's only on the red sides. So it also breaks the symmetry in space. And this will be very useful for what we want to do. Now, one nice thing about these topological ideas is that they are very transferable. So because it just depends on very simple features of the structure, you can find the same aspects, for instance, in a mechanical system, as shown here. And you can even move these defects around throughout the structure, which was the original idea already on the electronic setting, because also here, these defects can actually move when you have some kind of re-dimerization, these double bonds that can change around, and then this actually starts to drag along a charge of 1/2 of an electronic charge without a spin. So on the electronic side, this has some very nice features, and you see some of this replicated in completely different systems. And of course, you have different types of topologies if you look into different settings. For instance, if you look into two-dimensional systems, you find these states confined to the edges of say, a two-dimensional electron gas when you apply a strong magnetic field, and you find quantization, which is due to the finite number of these edge states. Again, the number is quantized. And you can then again replicate this in completely different settings, for instance, in photonic systems, which you build out of little ring resonators. There you suppress the couplings by building resonators in a very clean way, and you introduce phase shifts, which are similar to the phase shifts that the electron picks up in a magnetic field by just using the different lengths of these arms as the photon is moving around. Now, this was how topological photonics really started, the idea to replicate photonic effects, which are known for electronic systems. But this is already a challenge because the symmetries that we use in the electronic system, they are often fundamental, and they're often to do with the fact that the electrons are fermions. So for instance, their number is conserved. But for photons, that's not the case. So we can create them, we can destroy them. And in terms of the materials, we encounter gain and loss. But these are also, of course, interesting effects. So what I'm going to show you for most of this talk is that these are also useful effects. They change the way that we should think about these systems. We should extend our notions of topology to include these effects. But then sometimes these topological states become really visible in terms of really seeing them in the far field when you collect the light emitted by such a structure. I wanted to say one more word in terms of preparation, where this third feature of these topological states really comes in and how it matters. It is actually in the background of lots of effects that people are interested in, even though we don't really make this connection so strongly oftentimes. When we look at the system, which is this tight binding model, and we have this band structure, then we can break what is known as this chiral symmetry by putting on a staggered potential. What this does is really making a difference between the red and the blue dots, which initially are completely equivalent, which you see, for instance, if you just reflect the system. But with addition of this staggered potential, the system changes its behavior. The extended states, as a function of delta, if this is sort of the regions filled out by the extended states, this remains symmetric. But your topological defect state is only living on the red sublattice, so it only knows the value of plus delta. And it's even an exact solution with this energy just shifted to delta. So when you increase delta, then it will move upwards and it breaks the spectral symmetry. It's the only state that breaks the spectral symmetry. And you can see this by just looking at this plot. So this is a signature of a topological defect state. So we call this an anomaly, and it translates to other physical observables. In some systems, say in a higher dimensional system, you have a Bloch Hamiltonian, and at the place where I put delta, effectively a term appears which is just dependent on one of the wave numbers. And that means that if you plot the energy spectrum as a function of the wave number, you will find a dispersive mode, which is sloping into one direction. So it has, in this case, a positive group velocity, and there's no counterpart mode, which has a negative group velocity. So this becomes a directed channel, basically like an edge state, which is carrying current only in one direction. So the same anomaly is also giving us these effects that we know from, say, quantum Hall physics. But it could also be, there's another red line here, that your Bloch Hamiltonian does not depend on kz. These terms, they don't depend on kz. So then you find a whole set of states which have the same energy for all wave numbers, which is something that we call a flat band. So also flat bands can be understood by asking the question whether these additional states display this anomalous behavior or not, right? So all these different effects are really related to this simple third concept and underlying feature of these topological states. And you see this in many guises. For instance, in graphene, when you apply a magnetic field, you also get Landau levels, but in graphene, you also have a chiral symmetry. Graphene is also made out of carbon, but in 2 dimensions. But in there, you have 2 sublattices of, say, red and blue dots as above, only that they're arranged in a 2-dimensional fashion. And if you look at the zeroth Landau level, it happens to only sit on one of the 2 sublattices. At least this is the case if you look at one of these so-called valleys or K points, while this is the opposite in the other valley or K point. But you have the symmetry breaking in there as well. And so one question is whether one can realize these effects also in photonic systems and see this sublattice polarization. So this effect that states only live on one of the 2 sublattices, and furthermore can be confined also interestingly. So we will come back to these plots, but this is sort of defining some of the goals of this game. Right, so what I will show you is that there are lots of different settings that can be informed by this underlying principle. And this will allow us to confine states spatially, say in a microwave arrangement, or also in 2 dimensions, or in a micro laser, or we can use these quantum walks. And there are also acoustic and mechanical settings. So different perspectives, which hopefully as a sum total will give you an insight of what these systems are about. Right, so I start with sort of the original idea which drew me into this field, which was to replace the staggered potential by gain and loss. I knew there is a field in photonics which is known PT symmetric optics, in which people try to put gain and loss in such a way into a system, in a symmetric way into a system, so that the effects essentially cancel, but give you interesting modes. So on the frequency spectrum, you might still find that it doesn't change the lifetimes of the modes, even though you have gain and loss in the system, but you get interesting spatial patterns. And so I sort of naively thought, what happens? I want to have a PT symmetric topological system, basically. So you put in the gain and loss onto these systems on these sides, and then the first thing that you see is that the symmetry is actually broken. So the PT symmetry would rely that you have a sort of a reflection symmetry in your system, which maps the red onto the blue dots in a way that it interchanges gain and loss, but this is not possible if you also need to preserve the couplings. So if you preserve the couplings, then you have to reflect around this point, but this is mapping blue dots onto blue dots. So unfortunately, no PT symmetry, but there is another symmetry which is still preserved. And you see this if you plot the energy spectrum. So the extended states, if you just plot their real parts, you will still find that this is completely symmetric. And that this extra state that you had initially will still remain at the center frequency, so in the gap. The only thing that changes is that the imaginary parts break the symmetries. So if I want to also show the imaginary parts, I take every state that I have in the system. This will now be a complex frequency or complex energy, and I make a dot, and I find two lines, one which is coming from the extended states here, which fill this interval, and they all will have the same imaginary part. This translates to the lifetime of the modes, and the same happens for the other band. So in electronics, this would be the conduction band and the valence band here and here. And then you have this additional state, which, because again, it only lives on one of the sublattices, only knows of, say, the gain. If the red dots happen to have gain, it only knows of the gain of the system, and not of the losses that you put at the other positions. And now you have essentially a very simplified situation of amplification. In a normal system with many different sides and complex interference effects, when you put in gain and loss, all the modes will compete to be the one which has the longest lifetime. And once you increase the gain above a certain threshold, that one mode will become your lazy mode. What we now have is, by just looking at the general structure of the system, we know that if we put gain on every second side, there will be this particular mode which wants to be the lazy mode. Okay, so that's the simple idea. So this mid-gap state here becomes selectively amplified because of this anomaly in the sublattice polarization, and in this sublattice picture. That can be realized in many different settings. So I start out with the microwave experiment because that was really the first one. I know these microwave experiments have a very nice and interesting connection to Cuernavaca because of the Dirac oscillator. And it's essentially the same thing. So I mentioned it, I will explain it obviously completely, but you already know essentially what's happening there. So the group of Ole Kohle and Fabrice Montessagne, they bought these micro disks, these microwave disks, which can be operated in a regime where they essentially work as a tight binding site. And that's because in a certain frequency interval, you couple only into one particular resonator mode. And then you can space them out, and these modes become evanescently coupled. Now you can space them out in many interesting ways, and the Dirac oscillator is one way, but you can space them out just in the way as this tight binding model implies. And then that just translates into long and short spacings. And if you just have two long spacings, wide spacings in the middle, this defines your defect. Now, in these experiments, you can also use antennas to probe the system, send microwaves into the system and pick them up in a frequency resolved manner. And then you obtain what is the density of states. So this is the density of states, that's a function of frequency, first in a setting where you don't have the defect, and then you find a finite size quantization. I asked them to just put in 20 resonators because my whole idea was to show that this can be done in practical small systems, while theoreticians, of course, love large systems, but this is purposely done with small systems. So you find a quantization of 10 states coming from the valence band and 10 from the conductance band. Now, this is the situation where you have this additional site, and then you find this zero mode, the state at zero frequency in some ways, well, at the same frequency as the bare resonator frequency of these disks in the middle. And then they placed these elastomer patches on top of every second site. This is the idea of introducing a staggered potential, which is, in this case, just introducing absorption. So mathematically, that would be represented by an imaginary potential. And this is broadening out and suppressing all these extended states, but it keeps the spectral height and width of this zero mode. So that you clearly see this now in your spectrum. This translates into something in the dynamics. So if you take actually this system here with already the defect state and you launch a wave into it at the defect site, then yes, you couple very strongly into this mode, but you also have a finite overlap into all the other modes and you find a lot of speckle. But if you use the selective mechanism to suppress all the other modes, you find that the losses actually improve the signal propagation. So this is one of the games that you want to play. Now, the original idea of me was to actually sell this as a laser. And what I did, for instance, is to also see that this works if you do it in continuous space. You take a system which has little regions of different refractive index or dielectric constants, including an imaginary part in the dielectric constant, which models gain and loss. You work out the energy spectrum, which is now going to infinity. There are many, many bands. And then you will find that in every second band gap, one of these selectively amplified states lives. And in that year that I visited Cuernavaca, I mentioned it to Thomas already, it was a wonderful time when you could travel to many places. I also went to New York to a conference and met some experimentalists. And they were very, very kind to actually build this device a few years later. This is the group of Yang Feng. So they built a device based on micro-resonator rings, which are also spaced with small and wide spacings. And then you have modes which are circulatory, moving from one resonator to the other, but the coupling is again evanescent. And if you do this in such a structure without any further losses, then it becomes a multimode laser. You actually don't see really the difference of different spacings. It is just a man-made structure of many independent rings, which all want to laze. And so the mode competition is very complicated. The light that comes out is really very much structured. There are many peaks in there. But when you put in the losses, then you find just one spectral line, even though this is now still radiating from, this is a system with just 9 resonators. So 5 of them will now emit, 4 of them don't. And the spectral height is actually then improved. This is because there are also nonlinearities in the system. Lasers are such that if you have one clear winner of the mode competition, it actually takes all the energy. So all that energy that was here in the side peaks has been now moved into this one single mode laser by just putting losses into the system, right? Okay. And you can use this to build different devices, but I want to move a little bit on. So you can build two-dimensional structures of a similar fashion in which you can then, for instance, see the effect of flat bands and how they compete with these defect states. What is shown here is known as a leap lattice. And this is like a square lattice where you have removed a certain subset of points. Itself a square lattice, but it just covers a quarter of the points. And then you have these holes. And now if you look at the unit cell, this is just a periodic system, but already in the unit cell, you have more red dots than blue dots. So your Bloch Hamiltonian will now be a 3×3 matrix, but this chiral symmetry is actually still almost exactly present. Of course, there will be always some additional couplings. The chiral symmetry in these systems originates from the fact that red dots only couple to blue dots and blue dots to red dots, but there is no direct couplings between dots of the same color. It's not quite ideally realized in such a system because you certainly will have some couplings like this, while the couplings between the blue dots are actually quite well suppressed because they're in the shadow of another resonator. So there will be some additional couplings in there, but there will be between the red dots only. Without that additional coupling, you have this chiral symmetry. So you need to accommodate 3 eigenvalues for every value of your Bloch momenta. But that means that one of them has to be at 0 because you still have to have the symmetry. So you will have to have a flat band. Now, what we did is the normal leap lattice just has equal spacings or couplings between all the different components, but we corrugated in such a way, which you see here, to move them a little bit apart. So having wide spacings and small spacings alternating along these different directions, and then fusing 4 quadrants together so that you have large spacings around the center. That will mean that this will support a defect state, but this is actually living on the blue sublattice. So we have a flat band, which is living at 0 energy or close to 0 energy. And we have this defect state, which is living on the other sublattice. And what we can now do is to use the same selective processes to make this defect state more visible than the others. So what will help is a little bit these residual couplings between the red sides. They already introduce some dispersion into this flat band and separates this spectrally, but we want to go further than that. So this is how it looks like in these experiments. You find now it looks much more, I don't want to say messy, this is all recorded, right? So, but I love these experiments. So you find this, this beautiful spectrum where you find peaks coming from the different extended bands. Here you find a set of peaks that if you look at them spatially in the local density of states, you find them localized on the red sublattice, the one which has more dots. And then you find just adjacent to this, there we already use this with the spectral separation, the peak that if you look at it spatially would be in the middle of the system in this configuration, which I just had discussed. You can move this defect around. You can also move it into the corner so that you have the defect essentially here. And then you find it moving, the spatial pattern moving along with how you moved the resonators, the resonator defect. But again, you can suppress now the spectral weight of the states living on the red sublattice. You do it in the same way as before with elastomer patches. And then the spectrum looks like this. And this I really call beautiful because you have this, this peak, which is still living at the bare resonator frequency, clearly separated. And so you have actually suppressed all of the flat band in here because these are states which are only on the red sublattice. While the other states, they have some weight on both sublattices, so you still see them, but this is now nicely spectrally isolated. Okay, so for a little while, we'll just have variants. So there's just one more variant. So by repetition, that should be then clear enough, but you can build these structures also on a smaller scale using semiconductor devices again, but these now work as exciton polariton systems. So this is done in the group of Maurice Skolnick in Sheffield. You build these leap lattices by just patterning a structure. In there, you have a 2-dimensional electron gas, and you can put energy into this gas, which then populates photonic modes in this photonic crystal. It's a very complicated system in which you put a lot of energy somewhere high into some degrees of freedoms, and then it cascades down into photonic degrees of freedom or mixed degrees of freedom. These exciton polaritons, which are interacting because of the charges in there, and then this condensates. That's the analog of lasing in these structures. And what happens is that you find, if you analyze this in the far field, you can analyze this as a function of the wave number, depending on where you put your detector. You find that there are certain regions in which there is a lot of light coming out. And this then you can map out in space again. And sometimes this corresponds to a flat band, for instance, in this case here. So here you have a region which is sort of uniform over a certain interval at a roughly fixed energy. And the spatial pattern of this looks like this. This is mainly coming out of the red dots in the previous graphs. And so this is the flat band. And then you have other regions where you have a high density of states, say at the bottom of the first conduction band, at the top of the first conduction band. And you can distinguish this now by looking that you find intensity coming out of all of the resonators. Not out of the holes, obviously, because there is no resonator, but out of all these pillars. And then you can move further up in energy, and you find this is maybe not so clear in this plot, but you will see a more beautiful one next. Well, here it's still a bit messy, so why don't we look at the beautiful ones? Well, if you pump higher and higher, you really get this condensation going, and these lines become very, very sharp. Then these patterns become more and more clearly visible. And in this region of these high energies, you see that you find intensity only coming out of the flat band sides. So one sublattice, but not out of these ones here. These ones here, only out of these ones. And they have these lobes, which tells you that this is excited states. So they are like the P flat band. You would call this one S states, similar to atomic physics, and you would call these the P band flat states. They actually have a nice polarization pattern, because these lobes also correlate to the polarization of the light that is coming out. So it actually couples also a different degree of freedom. And therefore, I want to actually turn to another setting in which this polarization degree of freedom can be seen even more directly. But this one has to do with the different ways that you can create strong and weak couplings for different polarization degrees of freedom, but it's a bit technical. So instead of this, I will soon get to a setting in which the polarization degree of freedom will be used immediately. Okay. Now, but before that, I want to come back to this idea of what we saw in graphene. So in graphene, I had this slide where I said, if you have graphene and you apply a magnetic field, you get Landau levels, and they're spaced out similar to what is shown here. For instance, they're not equally spaced. There's some square root dependence of these spacings, but and it is symmetric because of this chiral symmetry. So neglecting higher order corrections, the A atoms only couple to the B atoms, but all other couplings are much weaker. So you have a chiral symmetry. And if you then look at the zeroth Landau level, it will only live on one of the two sublattices. Which one actually depends on the direction of your magnetic field. And it depends on which of these two so-called valleys you look at. So this is the pristine graphene band structure, which many of you will have seen, where you have these conical dispersion relations. Now, if you look at these two different regions in energy, you will find Landau levels at the two different sublattices, but there is an effect which essentially inverts the magnetic field if you go from one sublattice to the other one. And this is by replacing this magnetic field by a string. If you deform your sublattice, it will move around your cones in Dirac space. But for a theoretician, moving around something momentum is the same as adding a vector potential. And if that has a curl, then this acts like a magnetic field. Now, in these structures, when they're strained in these non-uniform ways, depending on which place you look, locally, the cones sit at different places. And so you get these pseudomagnetic fields. But these pseudomagnetic fields do not break time reversal symmetry. They are not putting anything imaginary into your equations. And that means that actually this guarantees that if you go from one of these cones to the other one, the pseudomagnetic field will have an opposite sign. But this means that if you simply do this business of creating Landau levels with a pseudomagnetic field in a photonic structure, you will be able to see one of the two sublattices. Okay, and this has been done also now in these experiments, actually in two different experiments, again by the group of Ulle and Fabrice. So we set out these structures, these microwave resonators in these strained fashions. And what they did is then to move the resonators around from an unstrained situation to a completely strained situation. And what you do in this way is you learn actually that you can only create these polarized Landau levels when you start out with a structure which has zigzag edges. That's an interesting configuration already in graphene, because people know that this supports edge states. And what you find is when you increase the pseudomagnetic field, these edge states become bulk states and they just remain on the sublattice. So this explains really the origin essentially of these polarized Landau levels from a way which people have not done before, connecting them actually to zigzag edge states. And what you also learn is that there's actually a maximal value of the magnetic field that you can create. If you want to have it uniform, it actually automatically cuts out such a triangle. And the reason for this is that in this strained structure, at some point, the couplings actually have to become zero. So you have to pull the resonators further apart and apart to achieve a pseudomagnetic field which remains constant, and it automatically cuts out this nice triangle. So topology is really nice because it connects lots of different aspects of a structure in a mathematically rigid way. And here it tells you if you do things with a pseudomagnetic field in honeycomb type of lattice, it will cut out a triangle, and the triangle will have zigzag edges. So it's so mathematics doesn't give you any choice, which is nice. And there is a counterpart experiment in which I was not involved by people in France, Alberto Amo and co, where they again realized this with polaritons. Okay, so sort of the last example that I want to show you with these effects tries to bridge this slowly into the direction of quantum mechanically interesting systems, where we would think about photons and maybe single photons. This experiment has not done with single photons, but we do a kind of tomography with the polarization degree of freedom, which just as much holds for individual photons. These systems are known as quantum vox, and what they consist of is an arrangement with in which you send wave packets of photons in different ways through beam splitters and fiber cables, so optical fibers of different lengths. And what you do there is to start out, split it into two, depending on its polarization. So you send this wave packet to this point, then you let one polarization pass and another one you deflect. You send it through different arrangements of different lengths so that they will have a different path length, that when they arrive at this position, they will be spatially separated. And the idea is to interpret this as 2 points on a tight binding lattice. But now we're going to mix these points, not by coupling, but by running the system, letting these wave packets run through the system multiple times so that they become recombined in different ways. And we will find interference effects, systematic interference effects in this. Indeed, we start with one wave packet, we go to 2 wave packets. In the next step, we will have 3 wave packets and so forth. But the ones in the middle will be recombinations of wave packets that we had earlier. And what one can do, these experimentalists, they can switch parts of these components around so that each wave packet has a different fate. So it sees a different optical component. And without going into all the details, this means that you have different couplings that you can color with different colors, and you can arrange them alternatingly with a defect in the middle. Okay, so this gives you the idea. The mathematics behind this will now be the multiplication of unitary matrices. So it's a bit different types of mathematics, but what is important is what comes out of this. What you will find is that there is a state that will be trapped. It will just jump between one of these two wave packet positions from one round trip to the next. So it will just jump from one to the other, but only if it has the right polarization. And the rule is the following. All the states that can extend over the whole system will have a linear polarization. And the state that is trapped will have a circular polarization, but only one of the two circular polarizations. So this is the way that symmetries are being broken in the system. Before we had it that extended states were living on two sublattices, and the defect state was living only on one sublattice. If you think about this in terms of spin, this reminds you of polarization, and the mathematics of spin and polarization is essentially identical. Okay, but what we have done now here is to really imprint this anomaly onto the polarization degree of freedom of these photons itself. Not just their position, but also their physical polarization. Not only the positions, but the thing that you see when you use a polarizing beam splitter. And that means that if you have this interface, you find this trapping only if you feed in a wave packet with the correct polarization. So if you match it to what you expect, otherwise you find that it starts to disperse out. While if you have a sequence of optical components switching always alternatingly, whatever polarization you start out with, the signal will just spread out. You can measure this polarization degree of freedom in different ways. As a function of angles determining on how you feed things into the system. And then you find that there is a certain beating with the topological interface. So this just tells you how well you fed your wave packet into the structure. And what this shows is the probability to remain in the center side after, I think, 12 steps, 12 round trips along this device. So first of all, without a topological interface, most of the weight will have gone away. There's some extrapolation to a very long structure. This is what is measured for, I think, 12 round trips. If you then have this topological interface, you trap much more, but how much you trap depends on an angle, which tells you which type of polarization you actually have sent into the system. It's an angle of an optical component, which is polarizing beam splitter. And then you can, I should maybe point it out where you do this, you can feed these photons out of your structure and send it again into a unit which is discriminating between the different polarizations and count them. And you can there then measure all the so-called Stokes parameters. It's essentially measuring spin in all possible directions. And what you obtain is a density matrix out of this. And this will now show that you have circular polarization. The circular polarization is seen by a phase shift of I between the measurements. So the real part and the imaginary part will be on different quadrants of this 2x2 matrix. It's a density matrix measuring linear polarizations. And in a basis of linear polarization, circular polarization is a phase shift of pi. And this is seen in these plots here, up here in the experiment, and down here how it should look like numerically. And it really looks identical. And Actually, if you let the wave packet go through the structure once more, its polarization degree of freedom happens to switch. So you can do it after one more round trip. And then you find that this actually has been switched around. Okay. Right. So this is really the main things that I wanted to talk about. There is many other things that I could talk about. For instance, there is now a new direction in which people have directed mechanisms of gain and loss. I just want to show you the idea of this. So this is what I showed you before. This is a completely reciprocal structure, which we have seen before in mechanics. And this is a reciprocal system, which means that the quality of the source is essentially the same as the quality as a detector. But what is interesting is to look at non-reciprocal systems in which you have unidirectional transport and directed amplification. So I know I don't have the time, so I'm just going to tell you that there is an interesting phase transition happening in these systems. But it's essentially related to this video here, which is coming from these experiments. I'm not involved in these experiments, but I'm very grateful to Jasper van Wezel, who introduced me to these. So these are experiments in which people have built a mechanical structure in which you have these rotors, and in there you have devices which are actually actively measuring the way that these rotors are displaced and changing the amount of force according to this, so that in one direction the force is actually increased further. So this is really actively measured by electronics, and there is a back action induced onto the system. And then you find that if you excite the system, it acts as a directed amplifier, as shown here. And now it happens that in these systems, if you want to work out the energy spectrum, you have a matrix and you look at its eigenvalues. And then there are eigenvectors, but there are two different types of eigenvectors, the ones that you multiply from the right or from the left to the matrix. What we see here is really the same as if you work out the eigenvalue that multiplies this matrix from the right. That's the thing that you see. Okay. Now the question is, what is the thing that you don't see here? And this is related to where do you actually excite the system? If you move your finger around into this direction, and the people didn't do it because they didn't ask the question, in one direction, there are two possibilities. You move your finger to the right, and if you excite the system here, it will react more and more strongly. Or it will start to, or it reacts less and less strongly. Okay. And that's actually an interesting phase transition, which I'm just flashing the slides for you. You can look at the formulas in your own time because it's all recorded. So all of this will be complete. Essentially, this is a system of coupled resonators. So this is a second order differential equation with a dynamical matrix. And the eigenmodes that you find can have this structure. They might both have the same profile into one direction, or they might have opposite profiles, where this U is the one that tells you how your system reacts. How strongly does it react, depending on how you put energy into the system. And the V tells you where do you see that it reacts. Okay, and these two things don't need to have the same profile. In particular, they don't need to have a large overlap. Now, there is a feature known in quantum optics, which is characterizing the overlap. It's very important for lasers, and it tells you how broad the line width of the laser is. And this object would diverge in these systems when you make them larger and larger, if you have this situation. So I've worked it all out. There are lots of formulas. But the important thing is that there is the possibility to obtain a huge response from these systems if you simply configure it into a situation where you have the so-called right and left eigenmodes localized at opposite ends of a system. Okay, so this is a bit of advertising of recent work. I don't want to go into all the details, but this is where I actually want to end. Okay, as an outlook, I've been very pleased. Well, I'm very grateful to have been asked to contribute to a topological photonics roadmap, which was edited by Hannah Price and co-workers and has just appeared in Journal of Physics Photonics. And this roadmap is actually wonderful. It's not because I'm part of it, but the idea of these people was wonderful. It's not a technological roadmap. It's a roadmap of what are the open physical questions, essentially, and of these systems, and also the experimental challenges that get along with. Out. Okay. So we have, I hope you can still hear me. My internet connection says it's a bit unstable. So we have all sorts of different platforms, and I didn't talk about many of them, just a few of them. And all of them, obviously, they have this aspect on the mathematical side of these anomalies, but on a physical side, what you try to obtain is some kind of gauge field. And so the pseudomagnetic fields, for instance, were an example of this. But in almost all of these settings, these gauge fields that we have at the moment are static. There are settings in atomic optical physics, like in traps, where you maybe have dynamical gauge fields, or you can rotate things around in different ways. But most of the time, there is no back action between the topological modes and things that move in the structure and the gauge fields themselves. So they just serve as a background. So my mission is to incentivize and make people interested in thinking about situations where the gauge fields actually have their own dynamics. They actually did in this original setting of this conjugated polymers, where the defect could move around and it was dragging half of an electronic charge, which is, of course, wonderful. So it would be nice to have similar effects in these man-made or person-made structures and see topological quasi-particles, but maybe based on structures which also have gain and loss and so forth. Okay, so this is basically the summary of this talk. I showed you lots of different variants of platforms in which you can obtain interesting patterns, and they're just reflecting topological features, especially this anomaly that is hidden behind these topological states. And I actually have lots of people to thank, but for some reason this slide didn't show up. Maybe I can show this up here. Okay, so this was hidden. That shouldn't have been the case. I have lots of people to thank. You can look at the names, and then I'm open. I stopped sharing. Okay, share screen. I hope you can see the screen again. These are all the names I have to thank. And yeah, and thank you for your attention.
Yeah, thank you very much, Henning, for this very, very nice, for this wonderful talk. It's really a pleasure. Are there comments, questions from the audience? Eduardo, please go ahead.
Okay, thank you. Really nice talk, Henning. Really interesting. This last part of dynamical gauge fields sounds really interesting. But I have a question related to this analogy to the spin and polarization. So you mentioned that, well, we can think in like the polarization similar to the spin 1/2, right? Mm-hmm. So is there any way to go to a larger value of spin in this analogy between polarization? Or do you know a way to extend this? Spin 1, spin 3.5?
It happens mostly if you think about the orbital wave patterns, if you think about Bessel beams of different order and these kind of things, and that's what people actively pursue. So it's a bit more difficult, and I can't think of something immediately with the polarization degree of freedom itself, because in atomic physics, what you do is you couple the spins by interactions, and you do representation theory, and you find all sorts of spins appearing there, but photons don't like to interact so much. So you would have to have something which as an intermediary, obviously. So it might appear in effective quasi-particles of a polaritonic nature, similar in these excitons, but I'm actually not an expert myself in excitonic polaritonic physics. I was happy that they were building these experiments. But if you think about these orbital angular momentum, it can also be nicely converted between polarization. There are wonderful experiments that people have done so that you can play things around, switching polarization from circular in one direction to the other, and at the same time increasing the angular momentum of your orbital wave pattern.
Okay, thank you.
Okay, are there further comments, questions from the audience? I have a stupid question. I did not get your argumentation. Why in this triangular shaped graphene nanoribbons you need zigzag edges to observe the zero lambda level? Can you repeat it?
Yes. Let me go back to it. It will take some time, I guess. So the we need to preserve our boundary conditions need to preserve all the symmetries, basically, that we have. And it happens that in these, one thing is a simple counting argument. So you need to have one lambda level that has a weight on only one sublattice. But you have a sum rule that overall, all the other lambda levels will have an equal weight. And there's a sum rule that you can only achieve this if you then have also more sites of that type in your system. And now if you, for instance, take zigzag edges, then you find that the lambda levels are actually, the zeroth lambda level will have twice as many states, but they're not sublattice polarized. And the reason is that the boundary conditions essentially break the chiral symmetry that you need in this case. The one that is also still valid in presence of the pseudomagnetic field. Now, this is important historically because the first experiments that had been carried out here, they were actually done with flakes that didn't have zigzag edges. And what these people also did is they never really measured anything in the bulk. So they only looked at the spectral height, things at the edge. But what they observed, you see that here, this is what they call the lambda level, the zeroth lambda level. It has twice as many eigenvalues than all the others next to it. So they actually observed this effect. Of course, they didn't quite know at the time that with these, which is sort of a mixture of many different, also generic boundary conditions, will not allow you to obtain these sublattice polarized states.
I see. I see. Okay, thank you very much. There's another question by Marco Antonio. Marco, go ahead.
Yes, hello. First of all, I really like the presentation. I found it to be really interesting. And I have a question that is partially related with the field I'm currently studying in my master's degree. So in recent papers, the flux of transverse energy along a multi-layer system of thin films have been proposed to be used for modulation of lasers. So do you think that this effect that you were studying could be applied here? Perhaps a certain order in the length of how we order these materials could be causing this?
Well, I think that there's always the connection between whatever you do, how beautifully new you think and very old physics. So if you think about distributed feedback lasers, people were already very clever to distribute their feedback in a layered structure and at the same time build a Bragg mirror. It was more working like a mirror, but if you look into the details, it also looks a little bit like the structures that we are talking here into the vertical direction of a VCSEL, right? So only that we try to do it in a way that we exploit the symmetries and think about this mode competition in this way. So yes, so I think that using layered structures serves a wonderful purpose. But if you need to think about it in terms of topology or not is the different question. And that's actually true for almost everything which I've encountered in topology. Almost everything is beautiful to link to topology, but you can understand the effects mostly by just looking at the equations without applying topology. So as an example, if you just think about these zero modes in these very simple structures, like the very first example here, oops, one step too far. If you just set the energy 0 in the system and ask to have a wave function which is only fired on every second side, you just get a recursive relation that you can solve. And you find that this decays exponentially. You don't need to know that this state appears because of topology. And so topology, I think, gives us inspiration to look into interesting structures and certainly helps us to classify them. But then there's also the practical side on it. And sometimes you understand it even better by forgetting about the topology. So, but it's an interesting question. I'm happy to learn more about what you're doing. Of course, I don't know the exact objectives of your master thesis.
Thank you very much.
Okay, there is another question by Rafael Mendes. He wrote the question into the chat. I want to ask about the possibility of study topological effects in aromatic molecules.
In aromatic molecules, so like benzene rings.
This is
I'm not
how
a
I understand it.
Chemistry is very, very long ago. So
this is
something like this, yes, I guess there will be a lot of things in there. I've not really thought about it. What have I seen? We built, I don't have it here, something like a benzene ring with a group of Alex Samite. We had a beautiful experiment, which I've not shown here. I could have shown it, where we put a pi phase into a hexagon, a single hexagon, and we just use an extra side in order to have a pi phase shift. And you could then launch waves along this and see how they interfered constructively or destructively at the other end. So because it's a reciprocal structure, the interference was confined to 0 or pi phase shifts, so it's quantized. So you can interpret it in topological ways. And now, maybe in chemistry, I know that there is a huge trend to, there is a quantum chemical approach to all of this band structure questions. And then they discovered that, I think it's systems which are maybe not completely topological, but show 0 modes. And there is this, it's not frustration. They found an effect in there, which they were better placed to identify with their quantum chemical thinking. So yeah, certainly interesting to think about.
Okay, yeah, thank you very much. Further questions, comments from the audience? Yeah, if it is not the case, I would love to make you to give another talk because of the topics which you just touched, and it's very interesting work. And but yeah, so hope to have you soon here in person again in Cuernavaca.
That would be also nice, yes. And we can talk offline, of course, and other ways, yeah. But oh, there is Marco still has his hand up. Do you have?
I think he left his hand up, Marco. Okay. Or do you want to make another question?
No, sorry, I just
okay.
read it up.
But I'm very grateful for the beautiful questions.
Yeah,
thank you.
And we are grateful for the beautiful talk. Thank you very much, Henning.
Okay, good.
And yeah, bye bye,
everyone.
and
bye-bye.
See you next week.